Hello, my name is Xingyue, and I will be present our work about AFUNet Cross-Iterative Alignment Fusion Synergy for HDR reconstruction via deep unfolding paradigm. Our research tackles a crucial task, high dynamic range image reconstruction. This involves merging multiple low dynamic range images, each taken at a different exposure, to produce a single HDR image with richer detail and a wider dynamic range. There are two main approaches to HDR reconstruction. The first is the alignment fusion method. Here, LDR images are first aligned to correct any misalignment caused by factors like camera shake or moving things. Then they are fused to create the HDR image. But these methods can lose information, especially in areas with loss of motion or extreme exposure differences. This is a big problem in dynamic scenes, where perfect alignment is nearly impossible, leading to lower image quality. The second approach is the fusion-only method. This skips the alignment step and directly combines the features of the LDR images. While it simplifies the process, it's prone to ghosting artifacts in dynamic scenes because it can't correct for misalignments in the input data. Despite their differences, both paradigms have a major limitation. They are often designed based on trial and error without a strong theoretical basis. This means they may not work well in different situations or handle real-world complexities effectively. Thus, we aim to introduce a new paradigm that can better leverage the synergy between the alignment and fusion tasks. As illustrated in this image, the visualized intermediate features of our paradigm demonstrate its ability to reduce artifacts and achieve superior reconstruction results. So let's move on to our contributions. First and foremost, we've introduced a unified MAP framework for HDR reconstruction. By formulating the problem within an MAP estimation framework and incorporating spatial correspondence priors, we've laid a solid theoretical foundation. This approach allows us to systematically break down the task into alignment and fusion subproblems, which work together to enhance overall performance. Building on this foundation, we've developed AFUNet, an end-to-end trainable network that takes this theoretical framework and turns it into a practical solution. AFUNet alternates between alignment and fusion in each iteration, ensuring that each step refines the output progressively. Finally, our extensive experiment has shown that AFUNet not only meets but exceeds the current SOTA. It can deliver visually superior HDR images with fewer artifacts and more detail. To sum up, our work provides a principled and effective approach to HDR reconstruction, combined a robust theoretical framework with a practical end-to-end solution that achieves SOTA performance. Let's talk about the key motivations behind our work. First, existing alignment fusion methods often suffer from significant information loss during the alignment process, particularly in overexposed or underexposed regions. This leads to less effective deghosting and a loss of critical details. Second, deep learning-based HDR methods are frequently designed empirically, lacking a strong mathematical foundation. This can impact their reliability and generalizability across different scenarios. Finally, we recognize the need for a structured model that can progressively align and fuse multi-exposure images. This approach will not only enhance the quality of HDR outputs, but also provide a more robust and reliable solution for real-world applications. These motivations guided us to develop AFUNet, which addresses these challenges through a principled and progressive approaches. First, we established the overall optimization objects for the entire task. We then decompose this overarching object into two subproblems, alignment and fusion. For the alignment subproblem, we employ gradient descent operators. These operators iteratively refine the alignment by minimizing the spatial correspondence priors, ensuring that the features from different LDR images are properly aligned. For the fusion subproblem, we utilize the HQS algorithm, which decouples the data fidelity term and the regularization terms, allowing us to solve for the fused features more effectively. By doing so, we ensure that the fusion process integrates the aligned features in a way that preserves detail and reduces artifacts. By addressing these two subproblems with traditional mathematical methods, we ensure that our approach is both theoretically sound and practically effective. Building on the optimization framework we established, we introduced AFUNet. This network transforms the traditional iterative optimization process into a learnable, end-to-end trainable framework, with each iteration unfolded into a network stage for progressive HDR feature refinement. In the initialization stage, input LDR images are projected into the feature domain using shallow feature extraction modules, providing the starting point for HDR feature reconstruction. The core of AFUNet consists of multiple stages, each with an alignment fusion module. The spatial alignment module aligns the features, while the China fusion module fuses the aligned features to enhance reconstruction. After all stages, the final HDR feature is obtained and projected into the image domain to produce the final HDR image. By unfolding iterative optimization into a deep network, AFUNet combines model-based and learning-based strength, achieving solid performance. This three tables shows the quantitative comparison results of AFUNet on three widely used datasets, including Kalantara's dataset, Hill's dataset, and Tail's dataset. We compare our methods AFUNet with classical and SOTA approaches, which includes CNN-based methods, transformer-based methods, and diffusion-based methods. As can be seen, AFUNet outperforms the other leading methods, achieving better reconstruction performance. Here shows the qualitative comparison results on these three widely used datasets. It can be seen that AFUNet achieves more complete scene reconstruction and retains more details, demonstrating strong reconstruction capabilities for challenging patches with a substantial reconstruction in ghosting artifacts compared to other methods. To assess the generalization capability of AFUNet, we evaluate the model trained on Kalantara's dataset and tested it on Terson's dataset, which lacked ground truth. It also demonstrates strong performance in generating high-quality HDR images with improved perceptual quality. Here is the ablation experiment of AFUNet as shown in this table, evaluating the contribution of each component within AFUNet. The results demonstrate the effectiveness of SEM, CFM, and DCM, with each component contributing to notable improvements in the performance of AFUNet. This table shows the ablation study on different stage numbers. We aim to investigate the impact of various stage numbers of unfolding iterative stages of AFUNet from 2 to 3 stages. It can be seen that fewer stages results in lower performance compared to the default configuration 4 stages. More stages, such as 5 or 6 stages, yield performance improvements, which demonstrating the effectiveness of our iterative design. To reach the performance and computational cost balance, we choose 4 as our default setting. This is all our presentation. Thanks for listening. Our code is already released on GitHub and you can get them the link.